Hi, I'm Shaymail Agat, and today I will be going to present friction in pipes. A little overview about this study is about friction losses in pipes and how they affect fluid flow. So when water flows inside a pipe, friction occurs between the water and the pipe surface, causing energy loss, which we call as head loss. So we studied two types of head losses. First is the major losses from straight pipes and minor losses from fittings like bands and valves. So we also analyze the Reynolds numbers to identify whether the flow is laminar, transitional, or turbulent. So as the flow becomes more turbulent, friction losses increase. Pipe roughness was also considered because rougher pipes create more resistance to flow. To calculate these losses, we use Darcy equation. So overall, these experiments help us understand how flow behavior and pipe characteristics affect hydraulic system. So to move forward, this is our theory. So as fluid flows through a pipe, it experiences internal resistance, as what I have said earlier, due to the viscosity of the fluid and external resistance caused by the roughness of the internal pipe wall. So these resistive forces result in the dissipation of mechanical energy, which is observed as a pressure drop or head loss along the length of the pipe. The fundamental mathematical model commonly used to quantify this major head loss in straight and uniform pipes is the Darcy equation. So this equation establishes that head loss is directly proportional to the length of the pipe and the square of the fluid velocity, while being inversely proportional to the pipe diameter. Consequently, higher flow velocity and longer pipe section produce greater friction losses, whereas larger pipe diameter helps reduce resistance to flow within the piping system. So to move forward, here is our materials. For these experiments, we used a hydraulic flow system to study friction losses in pipes. The study setup included several test pipes, particularly 20 millimeter pipe with a length of 3 meters. So a differential U-tube manometer was used to measure the pressure difference caused by friction inside the pipe. Flow regulating valves controlled the water discharge, while a collecting tank and digital stopwatch were used to measure the volume of water collected and the flow type. Additional instruments such as piezometer were also used for pressure measurement. So to move forward, here is our methods. The experiment was conducted using the SOLVE, the virtual lab simulator developed by the National Institute of Technology Karnataka Surathkal. So first, the 20 millimeter pipe was selected, and the other valves were kept closed. Water was then allowed to flow through the system, and the manometer was vented to remove trapped air before taking readings. So the head loss was determined from the difference between the manometer levels. To measure discharge, water was collected in the tank, while the time for the water level to rise from 55 centimeters to 65 centimeters was recorded using a stopwatch. Using the collected data, the flow velocity and Darcy friction factors were calculated through the Darcy equation. This procedure was repeated for 3 trials with different flow rates, of course, to observe the relationship between flow velocity, Reynolds number, and the friction loss. So table 1 presents the physical parameters and constant values used during the friction in pipes experiments. So these values were kept the same throughout all trials to ensure consistent and accurate result. So the test pipe used in the experiment had a length of 300 centimeters and an internal diameter of 2 centimeters. This dimension represents the pipe section where frictional head losses were analyzed. The collecting tank had an area of 3,500 square centimeters, which was important for calculating the volumetric discharge of water. So to maintain consistent measurements, the water level in the collecting tank was allowed to rise by 10 centimeters during every trial. So the initial water level starts at 55 centimeters and timing stop once the level reached 65 centimeters. So the time required for this rise was used to determine the flow rate and average velocity of the water inside the pipe. So the acceleration due to the gravity was taken as 981 centimeters per second squared, which is necessary in hydraulic calculation involving head loss and friction losses. So by keeping all these parameters constant, this experiment ensured that any changes in the calculated head loss and friction factor was mainly because by differences in flow condition and fluid velocity. So to move on to our table 2 presents the manometer reading, collection times, and calculated head loss for the 3 experiment trials. So the left limb and right limb readings from the differential manometer was used to determine the pressure difference across the pipe section. So from these valves, the corresponding head loss was calculated. For trials 1 and 2, the manometer readings were identical. The left limb reading was 24.50 centimeters, while the right limb reading was 29 centimeters. This reading resulted in the same calculated head loss, which is 56.70 centimeters. The collection time for both trials were also the same, which is 69 seconds, showing that the flow conditions remain similar. So in trials 3, there is a big difference. There is a change, so the right limb increased to 30 centimeters, while the left limb slightly decreased to 23.50 centimeters. So this created a larger pressure difference, which resulted in a higher calculation of head loss, which is 81.90 centimeters, and the collection time also becomes shorter at 55.50 seconds, indicating that the water flowed faster through the pipe. Okay, for our table 3 presents the calculated value of actual discharge, average flow velocity, and the analytical Darcy friction factor for the 3 trials conducted in the experiment. So trials 1 and 2 produce the same results. The actual discharge was 507.25 cubic centimeters per second, while the average flow velocity was 161.54 centimeters per seconds. This value resulted in an analytical friction factor of 0.0284. So in trial 3, the actual discharge increased to 630.63 cubic centimeters per second, which also increased in the average flow velocity to 200.84 centimeters per second. Even though the flow velocity and discharge became higher, the calculated friction factor slightly decreased to 0.0266. So this result showed that the increasing the flow velocity also increases the flow rate and the energy losses within the pipe system. However, the friction factor remained relatively consistent throughout the trials with an average value of approximately 0.03. So this indicates that the experiment maintained stable hydraulic conditions and consistent flow behavior during the testing process. Okay, to move on to our analysis of flow characteristic, figure 1 shows the relationship between the average fluid velocity and head loss for 3 experimental trials. So the graph clearly presents a positive trend between the 2 variables. So for trials 1 and 2, the average fluid velocity was about 161.54 centimeters per second, and the corresponding head loss remained relatively low and constant at around 56.7 centimeters. Trial 3, the velocity increased to approximately 200.84 centimeters per second, and the head loss also increased significantly to about 81.9 centimeters. So the result shows that as the fluid moves higher through the pipes, friction inside the pipe becomes greater. Because of this increased friction, more energy is lost, leading to a higher head loss. So to move on to the next characteristics. Okay, figure 2 illustrates the relationship between average fluid velocity and the analytical friction factor. So the graph shows the inverse relationship, meaning that as the fluid velocity increased, the friction factor decreased. So in trial 1 and 2, the average velocity was 161.54 centimeters per second, and the friction factor was 0.0284. In trial 3, the velocity increased to 200.84 centimeters per second, while the friction factor decreased slightly to 0.0266. So this behavior agrees with the principle shown in the Moody diagram for turbulent pipe flow. So as the velocity increases, the Reynolds number also increases, causing inertial flow forces to become stronger compared to viscous forces. So because of this, the resistance coefficient of friction factor becomes smaller. Okay, for our conclusion, to end this, the experiment successfully evaluated the effect of fluid velocity on head loss and Darcy friction factor in closed pipe system. So the results show that increasing the average fluid velocity from 161.54 per second to 200.84 centimeters per second also increased the head loss from 56.70 centimeters to 81.90 centimeters. So this confirms the direct relationship between velocity and energy loss described by the Darcy equation. So the experiment also showed an inverse relationship between velocity and the Darcy friction factor. As the velocity increases, the friction factor slightly decreases from 0.0284 to 0.0266. This behavior agrees with the Moody chart diagram for turbulent flow, where higher inertial forces reduce the effect of wall roughness on flow resistance. Overall, the experiment was successfully demonstrated the relationship between fluid velocity, head loss, and friction factor. These results were consistent with an established fluid mechanics principle, confirming the simulation accurately represented real hydraulic flow behavior. Okay, that will be all. Thank you. I hope you learned something. Bye bye.